You have studied that solids can be conductors, insulators and semiconductors based on their electrical conductivity. Substances like silicon and germanium are classified as semiconductors. Let's explore how they conduct electricity. Our objective is to understand the concept of semiconductors on the basis of band theory. We know that materials are mainly classified into conductors, semiconductors and insulators. Conductors are substances which exhibit good electrical conductivity, whereas insulators are those whose conductivity is almost zero. Substances that have a conductivity between that of a conductor and an insulator are called semiconductors. Elements like silicon and germanium are the most widely used semiconductors. All electronic devices such as laptop computers use semiconductors for accurate control of the current. Let us study the band theory to understand the concept of semiconductors. Consider a single isolated atom of silicon. It consists of 14 electrons which possess different energies. These electrons revolve in different orbits around the nucleus. Its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p2. As we can see here, 1s, 2s, 2p and 3s subshells are completely filled, while the 3p subshell is partially filled with 2 electrons instead of 6. The 3d subshell is completely empty. The outermost orbit in an atom along with its subshells is known as the valence orbit, and the electrons occupying the valence orbit are called valence electrons. Silicon thus has 4 valence electrons. Take a look at the energy level diagram representing different energy levels of the orbits or shells in an atom. Each line in the diagram represents a discrete energy level of the constituent shells. When 2 silicon atoms come close to each other, electrons in one silicon atom are influenced by the electrons in the other atom, as well as by the charge in the nucleus of that atom. The inner electrons interact weakly with each other. Hence, the magnitude of the change in the energy levels is less for electrons in the inner shells. To understand this better, take a look at 2 of the energy levels of silicon. When 4 silicon atoms are brought closer together, 4 different 3s and 3p levels are formed. In this manner, if we consider a silicon atom in a crystal, we can see that it is surrounded by a large number of silicon atoms. In this case, many different levels are formed as the crystal contains a large number of atoms. These energy levels are so closely spaced that they appear as continuous bands. Thus, different energy bands are formed for each energy level, such as 1s, 2s, 2p, etc. The width of each band depends on the interactions between the nearest neighboring atoms and not on the number of atoms. But the number of energy levels depends upon the number of atoms in the crystal. The energy band occupied by the valence electrons is called a valence band, whereas the energy band formed by the energy levels higher than those of valence orbitals is called a conduction band. Electric current flows in the solid when the electrons from the valence band jump into the conduction band. The gap which separates the valence and the conduction band is called the forbidden energy gap. Depending on the size of this forbidden gap, materials are classified as conductors, semiconductors or insulators. In metals, the valence and conduction bands either partially overlap each other or there is a very small forbidden energy gap. When a very small electric field is applied across the conductor, these electrons move freely in the conductor and carry current. Metals thus are good conductors of electricity. In insulators, the valence and conduction bands are separated by a large energy gap of about 5 electron volt. Hence, the electrons in the valence band do not have sufficient energy to cross the forbidden gap. Thus, no free electrons are available in the material, and therefore, insulators are bad conductors of electricity. On the other hand, in semiconductors, the forbidden gap is comparatively small. In the case of silicon, it is about 1.1 electron volt at 0 Kelvin. The electrons in the valence band do not have sufficient energy to jump into the conduction band, and hence a semiconductor behaves as an insulator at 0 Kelvin. When the temperature is increased, some of the electrons in the valence band receive sufficient thermal energy to jump to the conduction band. Application of a small electric field results in the motion of these electrons. Hence, the conductivity of a semiconductor increases with the increase in temperature. This type of semiconductor is called an intrinsic semiconductor. Conductivity can also be increased by adding certain impurities to the crystal. Such semiconductors are called extrinsic semiconductors. We will study both these types in detail under the topic of intrinsic and extrinsic semiconductors. That in conductors, the valence and conduction bands overlap each other, or there is a very small forbidden energy gap. In insulators, a very large gap exists between the conduction band and the valence band. Hence, there are no free electrons and insulators do not conduct any electricity. In semiconductors, the gap between the valence band and the conduction band is comparatively smaller, which can be overcome by supplying a small amount of thermal energy, which results in the conduction of current.